Hello and welcome to this lecture. In this lecture, I'm going to describe how you can use statistics when you conduct empirical studies. So imagine that you create a technique or a tool to, let's say, with the purpose to improve the productivity of software developers. But then you would like to understand if there is a real effect of using that tool on the productivity of the software developers. So you conduct an empirical study, let's say an experiment, and you start collecting data. And once you have all the data collected, then you apply some statistical analysis to understand if there is a real or significant effect of using that specific tool or technique on the productivity of software developers. So statistics is a sort of a tool that you use to answer some certain research questions, to understand if there is a certain effect of a specific treatment, or if there is a specific, let's say, effect by using a tool or a technique that you create with the purpose to improve, let's say, the process of software development or the productivity of software developers. Okay, so what are the learning objectives of this module? So you will learn how to perform basic statistical analysis using R. And R is a tool that can be used to conduct statistical analysis. Of course, there are other tools like SPSS and some libraries, Python libraries. But in this lecture, we are going to focus on R. However, you are free to use any tool that you would like when you conduct your research, for example, when you conduct your bachelor thesis. What is not in the scope of this course, so I will not let you know how to conduct empirical studies, so I will not teach you that. That's another specific story, another story. Basically, you need to, let's say, describe a problem that you would like to investigate, and then you have to describe the research methodology, how you are going to collect the data, how you are going to apply statistics, and how you are going to show the results. That's another story, and we are not going to talk about that. We will not also see how we can use R, in the sense that you will not learn how to use R in this lecture or in this module. Instead, you can learn how to use R by reading some, online material on the web. And I can say that it's very easy to use, so it's not very difficult. It's a sort of pseudocode that you are going to write and then run the code to see the results of the pseudocode that you have written to perform the statistical analysis. We will not also learn about the theory behind the applied statistics. Of course, for each one of the statistics that I'm going to show to you, there is a specific command to use or a pseudocode in R. I will not let you know what is the mathematical foundation or the mathematical story behind that specific statistics. But if you are curious about that, of course, you can read about it in the book that I will recommend in the next slide. So the studying material, basically the slides are required. So if you follow the slides, if you follow this lecture, then that's enough to understand how to apply statistics. But if you would like to have more information about the statistics and how to use R as a tool, then you can use this book, which is called the title is Discovering Statistics Using R. And the authors are Andy Field, Jeremy Miles, and Zoe Field. Very good. Regarding the assignments and the grading, so there will be one assignment related to this module, and it should be done individually. And the grading will be, either pass or fail. And of course, this is a sort of module. So this is an assignment for one module, which is, does not guarantee that you will pass, the course. Of course, this is, if you get a pass on this module, this is necessary, but not enough. It's not sufficient to pass the course. Of course, you will have different assignments to complete the course that you are following. Okay, so when it comes to the tool, the statistical analysis tool, so we have R, as I mentioned. So R is an open source environment for statistical analysis, and this is the website of the project, so you can access the website and read more about R. You can download R also by clicking on that specific link. And if you are also if you would like, that's optional, of course, you can also download R Studio, which is a sort of a visual interface for R. So then when you install it, then you will open the interface and write your pseudocode there, and then you conduct your statistical analysis instead of using, you know, the command line or the shell, let's say, if you don't use R Studio. So that's optional. Very good. So this lecture or this module is actually new. It's the first time that we introduce it in this course. So your feedback is very important. It's crucial to improve the quality of this module. So in order to support us, please just at the end of this lecture, of course, at the end of this module, please just answer this online questionnaire and provide us with the feedback so we can improve this module for future runs. And of course, I will have this slide at the end of the lecture, so you don't forget about it. Very good. So let's start with this module. So why do we use statistics? Why do we apply statistics? So we need statistics because we would like to answer some interesting research questions related to the empirical study that we are conducting. So as I mentioned before, imagine that you would like to understand the effect of a specific treatment, or maybe the effect of using one specific tool or technique on the, let's say, the process of software development, if it improves it or not, let's say. So that's sort of a specific question or a specific hypothesis that you would like to investigate. And to do that, you actually run, let's say, an empirical study, you collect the data, and then you apply statistics, which will help you to answer these interesting research questions. With the high probability, I think you will apply the design science research methodology when you are conducting your bachelor thesis, because one of the requirements for the bachelor thesis is that you are going to create an artifact, a tool or a technique, and then you need to evaluate it. And the way to do that in research is to conduct a design science research methodology. And how this works is that you start from the knowledge context here as a foundation. So you want to understand if there is a specific problem in the community, let's say in the domain that you are conducting research in. So you need to understand the knowledge out there, so you can read related, let's say, papers, related research regarding that specific phenomena, or let's say the domain that you would like or you are interested in investigating. So based on that knowledge, you will see that there are existing problems that could be solved. And then you will design or create a sort of a tool or a technique to, let's say, solve that problem. And based on this, let's say, artifact or the technique or the tool, you will need to evaluate this if it actually solves that problem. So, you know, there's a problem, you create a tool, but does it actually solve that problem? You need to evaluate that, you need to investigate. And to do that, you run empirical studies and you collect the data and you apply statistics, of course, to understand if there is a real effect or not. And then once you apply the statistics, you will provide new knowledge to the community, of course. You will say that, you know, I have developed that tool and this, I also conducted the evaluation. And we got this results, and this is, you know, these are the learned lessons that we would like to share with the community. So you will add a new knowledge to the body of knowledge that we have so far. But there might be also, when you investigate the tool that you have created, that you find new problems, or maybe there are certain challenges that you would like to address to improve the tool that you have created. So you go back to the design, let's say, space, and you, let's say, improve the design of your artifacts. So maybe you add something more, and then you go back and evaluate again if this actually solves the problem. So at the end, the design science research methodology is a sort of a cycle that starts with, you know, understanding the problem via the knowledge context. So you start with the knowledge base, with the knowledge body, and then you find some existing problems, you design a tool or a technique, you evaluate it, and then you share the result of the evaluations with the community. Very good. So now let's talk about the variables, because when you conduct empirical studies, you should understand what are the different types of variables. Okay, so we are going to see three different variables in this slide, and I'm going to define these variables to you, but in the next slide I'm going to provide some examples so you will better understand these variables and what's the meaning of these variables. First, we have the independent variable. The independent variable is considered to be the cause of some effect. So if you run or conduct an empirical study and you have a variable that is causing a certain effect, then this variable is the independent variable. And there might be more than one independent variable, of course. And it's called independent because its value does not depend on any other variables that you consider in your empirical study. Next, we have dependent variable. A dependent variable is actually considered to be affected or influenced by the change in an independent variable. And it's called dependent because its value depends on the cause, right? On the independent variable. And last, we can have confounding variables. And these variables actually influences or affects the relationship between the independent and the dependent variables. And these confounding variables actually are often controlled by the researchers because if you don't do that, you will make wrong estimations of the relationship between the independent and the dependent variables. So let's see some examples about these independent, dependent, and confounding variables. So suggest or imagine that we have this hypothesis. The hypothesis states that software models improve software quality. So this claim or this hypothesis says that if you use software models during software development, then these software models will improve the quality of the software that you are going to produce. So in this example, the independent variable is the software models, because these software models will cause an effect. And the dependent variable is the software quality, which is the variable to be affected or influenced by the cause or the use of software model. So the software quality will change according to the software models that are used in the software development projects. And then we have confounding variables. And these could be, for example, the type, size, and complexity of the models. So if we have, let's say, class diagrams, this could improve the quality or maybe not improve in a certain way, which could be different from using, for example, sequence diagram or maybe a use case diagram. The size of these models also could affect the software quality, right? If we have big models or maybe small models, this could be a sort of factor or a variable that could change the results or the effect that you observe in your empirical study. The time used to create or use these models. So if the developers, let's say, spend, I don't know, half an hour or 1 hour to understand these models, this could, might improve the software quality, but not as if you use these models for, let's say, 1 day or 1 week. That could be a difference. So there are different confounding variables that could affect the relationships between the independent variable and the dependent variable. Okay, so now we have seen the different types of variables. Now we are going to see the different levels of measurement of these variables. And we start with the categorical variable. So the categorical variable is made of categories. And for example, we can consider software models as a categorical variable because it classifies models into different categories like a use case, class, sequence, or deployment diagram. Another example is the nationality. The nationality can be considered as a categorical variable because it classifies the individuals into different categories like Swedish, Egyptian, or Chinese. The categorical variables or data can be used to consider frequencies or to count frequencies. For example, if you have, let's say, participants involved in a study, and you would like to understand how many bachelor students are involved in that study, then you only consider the bachelor students category. Of course, you might have other categories like master students or PhD students, but you are interested in understanding or knowing how many bachelor students are involved in that specific study. You might also ask a question about how many participants that are involved in this study are actually Swedish. So there might be, I don't know, 20 participants, and let's say 15 of them are Swedish, and the rest are from different other different nationalities. We have also the binary variable. So the simplest form of a categorical variable is actually the binary variable, and here we have only two categories. And for example, we might have a category that could be like alive or dead, so we have two categories. And also another example is, using models or not using models. So that's also another binary variable. Very good. The categorical variables that have more than two categories can be either nominal or ordinal. So the nominal variables describes the categories that do not have a specific order to them. And the ordinal variables describe categories that can be ordered or ranked. So let's see an example to better understand these two new variables. So a nominal variable, so for example, we have a variable that classifies software models into use case, class, or sequence models. So here we don't have any order, and this categorical variable can be a nominal variable. And then we have an example about the ordinal variable. So think about a variable that ranks the winning athletes with three ordered medals, so bronze, silver, and gold. So here we have an ordinal variable, which is the medal category, which can be bronze, silver, or gold. Another example is the variable that rank the experience of software developers into three different ordered categories. And here, let's say low, medium, or high experience. So in this case, we have an ordinal variable because the categories are actually ordered or ranked. Okay, we have also the interval variable. So the interval variable is, beside being an ordinal variable, so beside ordering the measurements, it also specifies that the distances between each interval on the scale are equivalent along the scale, so from the low to the high interval. An example of that, so think about the temperature that is measured in centigrade. This could be an interval variable where the distance between 92 degrees and 94 is the same or equivalent to the distance between 100 and 102. Okay, now we have the ratio variable. So it's the same as the interval variable, but in this case, any two values of the variable have a meaningful ratio, so making the operations of multiplications and division meaningful. So let's see an example to understand this ratio variable. So weight is a ratio variable because a weight of 6 grams is actually 3 times as heavy as the weight of 2 grams. So the operation of multiplication here is meaningful. Another example is that the score of 16 on an anxiety scale means that the person is likely twice as anxious as someone scoring 8. And again, here we have multiplication, which is significant and meaningful. So we have a ratio variable. As a counter example, think about the temperature in degrees Celsius. So if we have a temperature of 10 degrees Celsius, this should not be considered twice as hot as 5 degrees Celsius. So this cannot be considered as ratio variables. Why? Because if it were, then there will be a conflict, right? Because 10 degrees Celsius is 50 degrees Fahrenheit, and 5 degrees Celsius is 41 degrees Fahrenheit. And clearly here 50 degrees is not twice as 41 degrees Fahrenheit. Very good. When it comes to the interpretation of interval versus ratio variables, so you can consider variables to be interval or ratio according to your interpretation of a certain aspect. And to better understand that, we can have this example. So imagine that we have 2 people, Anne and Bob, and the salary of Anne is 6,000 per month, whereas the salary of Bob is 4,000 per month. So, and now we can ask questions. So how much more is Anne earning compared to Bob? If you say that, or if you consider that the difference between these 2 salaries by considering the subtraction, so you subtract the value between the 2 salaries, and then you say that the salary of Anne is actually 2Ks or 2,000 more than the salary of Bob, then you are considering the salary as an interval variable. On the other hand, if you consider that the salary of Anne is 50% more than the salary of Bob, then you are considering the salary as a ratio variable. So it's the way that you interpret these variables in your, let's say, context, then this will define the type of the variables that you are going to use. Very good. So now we have seen the different types of variables and the different levels of measurement of these variables. Let's see how we can describe the data that we are collecting when we are running empirical studies. So let's look into the descriptive statistics. Okay, so descriptive statistics actually provides a meaningful overview over the sample or the data that you collect from the empirical study. And it actually is the first step that you conduct in order to describe the sample or the data that you have collected through the empirical study. In this lecture, we are going to focus on the mean and standard deviation, which are used to describe interval and ratio data. And for the visualization of this mean and standard deviation, you often have to use bar graph that shows the mean and then minus and plus 1 standard deviation. Or maybe you can provide the data through a table. So you create a table that shows all the different descriptive statistics. So you have a column for the mean and then the column for the standard deviation for each one of the variables that you are going to measure. Or maybe you can provide or present the mean and standard deviation using a box plot. We have also the median and the interquartile range, and you use these descriptive statistics when you have ordinal, interval, or ratio data. And specifically, in particular, it's used when you have ordinal data. And to visualize this, descriptive statistics, the median and the interquartile range, you use box plots. Okay, so let's start with the mean. The mean value is actually also called average, and this value describes the central tendency of a given sample. So in R, the statistical analysis tool, if you use R, there is a function that calculates the mean value for you. And this function is, as you can see, called mean, and then you have two parentheses. And of course, we have to pass a parameter into that function, a variable, to calculate the mean. So here we have an example. As an input, you have a my data set, which is a set of different, let's say, numbers. And then you call the function mean, and then you pass as an input or input parameter the my dataset variable. And as you can see, the output is provided by the interpreter of that pseudocode, and as you can see, it's 5.5. The standard deviation is actually a complementary descriptive statistics to the mean value. If you measure the mean in your sample or data, then you have also to measure the standard deviation, and you also need to report these two descriptive statistics together, so the mean value and the standard deviation. The standard deviation is actually a measurement of how dispersed the data in relation to the mean value. So it provides indication of the distribution of the data around the mean value. If you have a low standard deviation, this means that the data are clustered around the mean. And if you have a high deviation, this means that the data are more spread out. In R, again, you have a function that calculates the standard deviation, and this function is called ST, and then you have, again, the parentheses. As an example, we have the same variable my dataset, which is a set of different numbers, and then you can call the function ST, and you can pass my dataset as an input parameter to that function. And as you can see, the result of that, let's say, pseudocode, you get the output, which is the standard deviation 3.02765. Another descriptive statistic that provides information about the central tendency of a sample or a data is the median. And the median is actually the number in the middle of a data set. And this is the middle of a series of values that are sorted from the smallest to the largest. Again, in R, the statistical tool, there's a function that can be used to calculate the median value. And this is called median. And as an example, as you can see here, we can call the median function, and we can pass the my dataset as an input parameter or input variable, and then we can run this pseudocode and get an output, which is here in this example 5.5. Okay, so we have the median as a descriptive statistic to describe the central tendency, and that's good. But we need to complement that with a description about the distribution of the data around the central tendency. And to do that, we need to calculate the interquartile range. To understand the interquartile range, we need to talk about the quartiles first. So the quartiles actually measure the spreads or the distribution of the data above and below the median value. And these quartiles actually divide the distribution of the data into 4 groups. So we have different quartiles, Qs, as you can see here. So Q0 represents the minimum value in the data set. So for example, imagine that you have a data set that is consisting of numbers from 1 to 10. Then the minimum value here will be 1. Then we have the first quartile, Q1. So the first quartile actually represents the first 25% of the data. And then we have Q2, which is the second quartile, where you can find the first 50% of the data. And then we have Q3, which is the third quartile, and under which you can find the first 75% of the data. And last, we have the Q4, which is the maximum value in the dataset. So I said that these quartiles, these Qs actually here divide the distribution into 4 groups. So the first group is between Q0 and Q1, so the first 25% of the data. The second group is between Q1 and Q2, which is between the 25 to the 50% of the data. The third group is the group between Q2 and Q3, so between 50% and 75% of the data. And last group, the fourth group, is between Q3 and Q4, which is from the 75% to the 100% of the data. So to calculate the interquartile range, you need to subtract the value of Q1 from Q3. So it's the, let's say, the set of data between Q1 and Q3. And this actually contains the middle 50% of the data. Let's have an example about the how to show the quartiles and the interquartile range using the R statistical tool. So again, here we have a function that calculates the IQR and also the other quartiles, and it's called quantile in R. So again, here you call the function and then you pass the variable myDataset, and then you will get the results. As you can see from the output, you can see the minimum value, which is 1, which is the 0%, as you can see described in this example. And then you can see the maximum value in myDataset, which is 100%. And then you can see the first quartile, 25%, which is 3.25. The median or the second quartile, which is 5.50, and then the third quartile, which is the 7.75. And here, if you want to represent the interquartile range, then you have to say Q3 minus Q1. So you have the value 7.75 minus 3.25, and the subtraction of these two will give you the value of the interquartile range. Okay, so to represent or visualize descriptive statistics that you have created in the previous steps, you can use different visualizations. So for the median and the interquartile range, you can create a box plot. To create that in R, you can call a function which is called box plot. And here, as you can see in this example, we can call the function box plot and pass the input variable myDataset to that function, and as an output you will get these box plots. This is the visualization that you will get from running this pseudocode. So as you can see here, we have the box plot. Here we have the minimum value. Here the minimum value is 1 according to the dataset, and here you have the maximum value. So this line represents the maximum value, which is 10. And then here in this box, we can see the distance between the first quartile and the third quartile, which is the interquartile range. And then here, the thick line in the middle is the median value. And here in the box plot, we have also an upper whisker and a lower whisker, which represents the scores which are outside of the middle 50%. So the upper 25% and the lower 25%. Okay, so now we have seen the descriptive statistics, and you know how to calculate the mean value and the standard deviation. But also you can calculate the median and the interquartile range. You can also use the visualizations. You can create a box plot to represent the descriptive statistics. Now let's talk about the hypothesis and the significance level. You know that it's very important to formulate and define the hypothesis when you are conducting empirical studies. And it's also important to understand the significance level, because at the end you want to understand if there is significance influence of the independent variable on the dependent variable. So let's see how we can formulate the hypothesis. What are the null and the alternative hypotheses, and what is the significance level, and what is the p-value. Okay, so when you conduct an empirical study, you have to define the hypothesis. And basically for each claim that you do, you have to state the null hypothesis and then the alternative hypothesis. And these two are actually competing claims, and you run a statistical test to understand whether one of them is the case or not. So you would reject one of them and accept the other one. In this example, as you can see, we have a null hypothesis, which is software models do not improve software quality. So we have this as the null hypothesis. And then we have an alternative hypothesis, which is software models do improve software quality. So in order to understand which one is the case, then you need to run the statistical test. And based on the statistical test, you will accept or reject the hypothesis that you have for this claim. Okay, very good. So we have defined the hypothesis, the null and the alternative hypothesis. But now, before conducting the statistical test, we need to set the significance level. And the significance level is important because based on this, you will weigh evidence against and for the hypothesis that you have defined. So the significance level is often called alpha, and alpha is the probability that you will make a mistake of rejecting the null hypothesis when it is actually true. So the null hypothesis is true, but you make a mistake of rejecting it. Low significance level, so if you set a low significance level, this will reduce the risk of making a type 1 error, so rejecting a true null hypothesis. But a low significance level will also increases the risk of making a type 2 error, which is failing to reject a false null hypothesis. So you have a null hypothesis, which is a false, but you fail to reject it, and you commit a type 2 error. And conventionally, actually, alpha is often set to 0.05. So researchers does that when they conduct empirical study. And the aim is to have the balance between these two types of errors. So you don't commit type 1 error and you don't commit type 2 error. Okay, so we have seen the significance level, but what about the p-value? So when you conduct the statistical test, you often get a p-value as a result of that test. And the p-value is actually a value between 0 and 1. It is a probability. And it quantifies how confident we should be that there is an effect, or if there is a difference between the two settings that we are comparing. So in our case, if using software models do not improve software quality, or if using software models will improve the software quality. So as we can see that here, if we have a p-value that is greater than alpha, so if you remember that alpha is often set to 0.05, this is the convention, this is commonly used. So if the p-value is greater than alpha, which is 0.05, then you accept the null hypothesis and you say that there is no difference, there is no effect. That's the null hypothesis. And if the p-value is less than alpha, less than 0.05, then you will reject the null hypothesis. You will reject that there is no difference, and you accept that there is a difference, or maybe you say that there is more likely that there is a difference between the two settings that we are comparing, or there is more likely that there is an effect of that specific treatment that we are applying. So let's see an example about this p-value. So here we have two hypotheses. We have the null hypothesis and the alternative hypothesis, as we have seen before. So software models do not improve software quality. That's the null hypothesis. And then we have software models do improve software quality. That's the alternative hypothesis. And we have set the alpha level, the significance level, to 0.05. After that, we conduct the statistical analysis. We run a specific test, and let's say that the calculated p-value is, for example, 0.03. So we can see that the p-value is less than the alpha. So we reject the null hypothesis and we state that there is an effect or there is a difference. So the software models do actually improve the software quality. Okay, comparing two means. Comparing two means is actually a way to understand if there is a difference between two samples. So imagine that you want to understand if using models actually improves software quality. So to do that, you conduct an empirical study, you conduct, let's say, an experiment, and you have two groups of developers. Let's say 50 developers will use models to create software, and then you ask other 50 developers to create software without using models. And then based on the samples or the data that you collect from these developers and the software that you have developed, then you will conduct some statistical analysis and you will see if there is a difference between these two samples. You will compare the difference between the means of these two samples. So there is a number of statistical tests that can be applied to compare the two means. And of course, there are different conditions to select between these tests, which we will see in the next slides. Okay, so to compare the means of two samples to understand if there is a difference between the two samples, you can select from different statistical tests. But to select the right test to perform, you need to pay attention to different conditions. And the first condition to look at is to understand if the samples are actually independent or dependent. Okay, so we want to compare two means. So which test we have to select? In the first case, let's talk about the independent samples. So if we have independent samples, what test we can select and use to analyze the data? So you have independent samples when there is no direct link between any of the measurements in your samples. For example, if you have two groups of developers doing some activities, let's say they create software and you would like to understand if the software that they have created is actually of a good quality. If the developers in the first group are different from the developers of the second group, then you will have independent samples because we have, data coming from different people. So that's an example of having independent samples. For using the different tests, so we have two cases here, case 1A and case 1B. So for the case 1A, you can use a test called a t-test if certain assumptions are satisfied. First of all, if the samples that you have measured or collected are normally distributed, and we will talk about the normal distribution in the next slide. The samples are measured at least at the interval level, so you have interval data or ratio data, and we have talked about that in the previous slides. The samples have homogeneous variance, and that's also assumed only in theory, and we will check that in the next slide also. If the assumptions are not satisfied, so if the assumptions for running the t-test are not satisfied, then you have to use the non-parametric Mann-Whitney test, which is also known as the Wilcoxon-Rank sum test. Okay, so we will see examples about how to run t-test in R in the next slide in this lecture. But also we'll see examples about how to run the non-parametric counterpart, which is the Mann-Whitney U-test. But now let's talk about the normal distribution. So what is the normal distribution? And of course in R there is also a command or function to check if your data or samples are normally distributed. So we will see that also later. So in a graphical form, the normal distribution appears like a bell form, as you can see here in this example. And it shows that the data near the mean are more frequent in occurrence than the data that are far from the mean. So in this example, as you can see here, we have on the x-axis the height of people. So we have short, average in height, and tall. And on the y-axis, we have the probability of observing, short people. and average people and tall people. And as we can see here from the data that to observe, to find a person that is very short is less likely, it's very rare. And to observe a person that is very tall, it's also less likely, it's very rare. But to observe and find people that they have the average height, it's more likely. And as you can see here, the data that are around the mean, we have more frequency in the occurrence. And in this way, you will see that if you plot the data, if your samples and they have this shape of a bell curve, then you have a normal distribution. Okay, so to check if the data are normally distributed, we can run the Shapiro-Wilk test. And in this test, actually, we assess whether the sample is likely to originate from a normal distribution. And the null hypothesis of this test, H0, states that the sample comes from a normally distributed population. To perform this test in R, so we have this command, so we have to write Shapiro.test, and then we pass the samples that we have to check if they are normally distributed or not. And once we run this test, we will have a sort of an output, and we need to look at the p-value. So there is a value labeled the p-value, and if the p-value is greater than the alpha, the significance level that we have set before, which is 0.05, then we can accept the null hypothesis and we say that the data are normally distributed. Okay, so now let's talk about the homogeneity of the data. In R, the statistical tool, there is a command to calculate the homogeneity of the data, and we will see that later in the slides and the examples. But what about the concept? So recently researchers stopped from testing these assumptions, and this is for two reasons. First of all, this assumption actually is relevant if you have unequal group sizes. But if you design your experiment, let's say, and you have equal group sizes, then this assumption is not relevant anymore. The second reason is that you have to test for this assumption if you have a small sample size. But if you have large samples, so a large sample size, then these assumptions will be also irrelevant. However, if you use R, and if you want to use the t-test, so in R, when you perform the t-test, the tool by default runs a Welch t-test. And the Welch t-test here is sort of a test that conducts an adjustment already, which is able to correct the violation for this assumption. So if you conduct the t-test in R, it will run the Welch t-test, and you don't need to account for the homogeneity assumption. But of course, you have to talk about it in theory if you run this test. Okay, so how we can check for the homogeneity of variances? There's a test that is called Fisher's F-test, and this test actually checks if the variances of two samples are equal. But this test assumes that the samples are normally distributed. So you have to check first if the samples are normally distributed, and then you can run or conduct this test, the Fisher's F-test. The null hypothesis, H0 for this test, states that the variances are equal. And to perform this test in R, you can write this pseudocode. So we have var.test, the function test, and then we pass the samples as parameters. In this example, we have data 1 and data 2. So once we conduct this test, so once we run this pseudocode, we will get an output. And from the output, we can check for the p-value. And if the p-value is greater than alpha, which we set to 0.05, as we have mentioned earlier, then we accept the null hypothesis. Then we say that the variances are equal. Okay, so we have seen the assumptions for conducting the independent t-test. We have seen how to check for the normal distribution. We also have seen how to check for the homogeneity of the variances. So now, if we have all the assumptions satisfied, now we can conduct the independent t-test. So this test actually compares two means when this means actually belongs to two different groups of entities. For instance, you can think about running or conducting an experiment where you have two conditions, and then you involve or ask different participants or developers, for example, to be part of these two conditions. So you don't have any relation or connection between the samples that you collect from these experiments, and that's why it's called independent t-test. To conduct this test in R, so we can write this pseudocode t.test, and then we pass the samples as parameters, in this example data 1 and data 2. Again, we look to the outputs and we check the p-value. If the p-value is less than 0.05, then we can say that the means of these two groups or samples are significantly different. In case that the assumptions for conducting the independent t-test are not satisfied, so we have the data or the samples that are not normally distributed, or if the variances are not equal, then instead of running the independent t-test, we run the Wilcoxon rank sum test. To conduct this test in R, we can write this pseudocode wilcox.test, and then we pass the samples as parameters. And again, we look to the p-value. If the value is less than 0.05, then we can say that the means of the two groups are significantly different. Okay, so let's talk about the second case when the samples are dependent. So the samples are dependent if there is a relation or connection between the measurements of the data that we have. And this could be, for example, if you measure a variable before or after a specific event. So imagine that you measure a variable, and then after a specific event you apply a treatment, remove a factor, or add a factor. So the measurements that you collect are dependent in this case. Another example is when you conduct longitudinal studies. So when you are interested about how the variable evolve over time. So you take a measurement of the variable at a time t, but then you take another measurement after, let's say, 5 months, 1 year, etc. And then you compare the results. So here we have a sort of dependency or relation between the measurement that you do. The third example is when you use a within subject design or repeated measure design. So this is a design when you conduct empirical studies, for example, experiments, where you plan to involve the same participants or the same subjects into two different conditions of the experiments. So imagine that you would like to understand if using models improve the software quality, then you use or involve some developers, but you use them into the two conditions. So in the first condition, you ask the developers to create software without using models. Okay, and then you ask them, the same developers, to create software by using models, and then you compare the differences. So this is a sort of an example that shows how the samples could be dependent in this case. Similarly, for the case 2, when the samples are dependent, we have also two subcases, case 2a and case 2b. So first of all, we can use the paired t-test if the following assumptions are satisfied. And again, here we have the same assumptions. So if the samples are normally distributed, if the samples are measured at least at the interval level, interval or ratio, and the samples have homogeneous variances. So if these assumptions are satisfied, then we can run the paired t-test, which is for the dependent samples. If these assumptions are not satisfied, then we conduct the non-parametric test, which is the Wilcoxon signed rank test. Okay, so the paired t-test or the dependent t-test actually compares two means, but these means actually come from the same entities. So there is a relation or connection between the measures that we get from the experimental conditions. And to perform this test in R, we can write this pseudocodes t.test, and then we pass the two samples as parameters, data 1 and data 2. And then we have to specify that this is a paired t-test. So we write paired equal to true. We look to the outputs, and if the p-value is less than 0.05, then we can say that the means of the two groups are significantly different. If the assumptions for conducting the paired t-test are not satisfied, then we can run the Wilcoxon signed rank test. To run this test in R, we can write this pseudocode wilcox.test, and then we pass the samples as parameters, data 1 and data 2, and then we have to specify that this is a paired Wilcoxon signed rank test. So we say paired equal to true. And then we look to the output, so we look at the p-value. If the p-value is less than 0.05, then we can state that the means of the two groups are significantly different. Okay, so this slide summarizes the different tests that you can run to compare two means in R. So first of all, we have the Shapiro-Wilk test, which checks for the normality of the data, so if the data are normally distributed. So imagine that we have two samples, data 1 and data 2, then we can conduct the test of normality using this command, shapiro.test. And then if you want to conduct the test for checking for the homogeneity of the variances, we have the Fisher's f-test. And this is the command, var.test, data 1, data 2. And then we can check if the samples are independent. We run the t-test as follows. But if the samples are dependent, then we run the paired t-test as follows. And if the assumptions for the t-test are not satisfied, we run the Wilcoxon rank sum test. And if the assumptions for the paired t-test are not satisfied, then we run the Wilcoxon signed rank test. After we calculate if there is a difference between the means of two groups, we also have to report the effect size of this difference, which could be a small effect, medium, or large effect. First, if we consider the t-test, which is the independent t-test, and the paired t-test, which is the dependent t-test, and those are parametric tests that requires that the data are normally distributed, we can use this formula to calculate the effect size. So here the effect size R equal to the square root of t squared divided by t squared plus df. And the t here is the t statistic, which is the ratio of the departure of the estimated value of a parameter from its hypothesized value to its standard error. And of course, this is a theoretical part that, of course, if you would like to understand more, you can check and read about it. The df is the degrees of freedom, and this represents the number of independent pieces of information used to calculate a statistic. And of course, we will see how to calculate this effect size using the R statistical tool. Considering the non-parametric tests, the Wilcoxon rank sum test and the Wilcoxon signed rank test, and here, as we said, non-parametric test, which means that the data are not normally distributed. So to calculate the effect size here, we have this equation, R equal to Z divided by the square root of N. Z is the Z-score. It is a measure of how many standard deviation a value is from the mean of a given distribution. And N is the sample size, or the total observations that you do. And of course, we will see also how to calculate this effect size using the tool, the R tool. So we have calculated the effect size. So now we have to say if it's small, medium, or large. If R is about 0.1, then we say that we have a small effect. If it's about 0.3, then we say that we have a medium effect. And if R equal to 0.5 and above, this means that we have a large effect. And this is a sort of commonly used by the researchers to report the effect size of the difference in this case. Okay, so now we have all the tests that can be used to compare two means. Let's now see an example together, and we conduct some tests using the R tool. So in this example, let's say that we have a researcher that wants to investigate whether the use of software models actually influences the software quality. So in the first step, the researcher sets or formulates the hypothesis, the null hypothesis and the alternative hypothesis. The null hypothesis is that software models do not improve software quality. And the alternative hypothesis is that software models improve software quality. So once defining the hypothesis, then the researcher designs an experiment. And in this case, the researcher designs a between-subject experiment. Between-subject experiment means that the subject used in one condition of the experiment are different from the subjects that are used in the second condition. And this is actually a version, but there's also another version called within subject. And in the within subject, actually use the same subjects in the two conditions of the experiment. So here we have two settings or two groups. So the first one is not using models. And in this group, we have 25 developers that do not use models. And the quality of the final software that is created by these developers is evaluated. So we have 25 developers do not using models, and we measure the quality of the final produced software. In the second setting or a group, it's called using models. We have different subjects, different 25 developers, but in this case they use models and the quality of the final created software is evaluated. So for this example, I have created two files. So we have the models.csv file, which contains the data that are collected by the researchers. So data about the quality of the final created software and the condition if these developers used or not used the models. And then I have another file called code.r, where we will see all the test or the statistical analysis that we are going to do or perform using the R tool. Okay, so now you can pause this video and then you can run the video that shows the example about how to compare two means. We have seen how to conduct the statistical test to understand if there is a difference in the mean between two groups. And now we are going to see how we can report these results. So how we can write them, let's say, in a report. For the t-test and the pair t-test, so for the independent t-test and the dependent t-test, we can use the following. So the following is an example based on the hypothesis that we have investigated together in the example before. So here we can, let's say, report the results as follows. So the use of software models improves software quality, and we report the mean value and the standard deviation value in comparison to not using software models. And here we report the mean value for that specific group and the standard deviation for that specific group. And then we say that the difference is significant. The p-value is equal to, we report the p-value because it's less or smaller than alpha. It's a significance level, 0.05. And then we report that the effect size is, of course, large here because, as you can see, r equal to 0.7, which is larger than 0.5. And of course, here it depends on the examples that we have found. But of course, if there is, if the p-value is greater than 0.05, then you say that the difference is not statistically significant. Very good. When it comes to the Wilcoxon rank sum test and the Wilcoxon signed rank test, so the non-parametric versions of the t-test and the pair t-test, instead of reporting the mean and the standard deviation, we report the median instead, since it is more appropriate than the mean for non-parametric tests. Okay, so in this lecture we have seen how to compare two means. But if you are interested in knowing how to compare more than two means, let's say three means, then you can conduct different tests. So you can conduct the one-way ANOVA test. And this test actually requires that the samples are normally distributed, so you have to check that assumption. If this assumption of normality is not satisfied, then you can conduct the Kruskal-Wallis test, which is the non-parametric counterpart of the one-way ANOVA. To have more information about these tests or how to compare more than two means, then you can read the book. So there is this reference, Discovering Statistics Using R, by Andy Field, Jeremy Miles, and Zofield. Okay, so in the second part of this lecture, we will talk about correlations. So if you would like to check if there is any correlation between the variables that you have at hand, then there are different or several correlation tests to choose from. And of course, there are assumptions, so you have to check these assumptions. And if certain assumptions are satisfied, then you select one correlation test. Otherwise, you go to the next one. So in the next slides, we will talk about this correlation test, and we will see also an example on how to conduct this test using the R statistical tool. Okay, the variables can be correlated in different ways. They can be correlated positively, they can be not related at all, or they can be correlated negatively. So let's see some examples to understand these different options. First, the more I practice my guitar, the better a guitar player I would become. So here we can see that we have a positive correlation, because as I practice more, I would become a better guitar player. So one variable goes up and the other one also goes up. Second, not related at all. As I practice the guitar, my playing ability would remain completely constant. So this means that it does not matter how much I practice the guitar, I will remain the same, so we don't have any correlation. And third, we have the example, the more I practice my guitar, the worse a guitar player I would become. So this would never happen in reality, but this is an example to show you that there might be that you have a negative correlation between two variables. So one variable goes up and the other one goes down. So the relationship between the variables can be expressed statistically, and also when you run the correlation test, as an output you will get also the correlation coefficient. And this coefficient can be between -1 and +1. If the coefficient is negative, then you have a negative correlation, and if the coefficient is positive, then you will have a positive correlation. The correlation coefficient provides information about how strongly the variables are correlated to each other. In this example, we can see different scatter plots that represent the different values of the correlation coefficient. But let's start by reading this table here. So the strengths of the correlation can be weak, medium, or strong. And then the correlation coefficient can be positive or negative. So when we have it a positive, then we have a positive correlation. And when it is a negative, we have a negative correlation. So a weak correlation, we have the coefficient value between 0.1 to 0.3. If we have the coefficient between 0.3 and 0.5, we have a medium correlation. And then if we have a coefficient of value 0.5 to 1, we have a strong correlation. Actually, 1 represents a perfect positive correlation, and -1 represents a perfect negative correlation. So in this scatter plot, as we can see, the first one provides, as we can see, that the x value increases and also the y-axis increases. So the variables are, let's say, correlated and positively. So here we have a strong correlation. And here in the second one, we have a sort of a medium correlation. So we have the different data points. They are not perfectly aligned. Here we have a weak correlation. We can see that there is a tendency that as the x values increases, also the y values increase. So we have a positive correlation, but this is weak, as we can see from this scatter plot. Here, when the coefficient correlation is equal to 0, so there is no relation at all between the variables. So we cannot see any, direction that we can fit this data and see if it's linear or not. Here we have the negative correlations. So again, here we have a weak negative correlation. As the values of x increases, the values of y decreases. And here we have a medium negative correlation, and then here we have a strong negative correlation. And if we have a value of -1, then we have, as we said, a perfect negative correlation. Okay, so to conduct the test of correlation, we have different tests to choose from. We have Pearson, Spearman, and Kendall. And of course, the selection of one over the another depends on certain assumptions, and we will see this test and their respective assumptions and how to conduct them using the R statistical tool. Okay, so the first correlation test that we are going to look at is the Pearson correlation. And here we say Pearson's R. So R here is the correlation coefficient. This test is a parametric test, and when we say parametric, this means that this test requires the normal distribution assumption. So the Pearson correlation test measures the linear relationship between two variables. And the assumptions for conducting this test are the following. So the variables should be normally distributed, and the variables also should be measured at the interval level, and the variances are relatively similar. So the second correlation test that we can conduct is Spearman correlation, and the correlation coefficient is called rho. And this is actually a non-parametric counterpart of the Pearson's correlation. So if the assumptions of the Pearson's test are not satisfied, then we use the Spearman correlation. So if the data or the samples are not normally distributed or the variances are not relatively similar, then we can use the Spearman correlation. The third option that we can conduct is the Kendall's correlation. And the correlation coefficient of the Kendall correlation test is called tau. So when we talk about the correlation, Kendall's correlation, we talk about Kendall's tau, basically. And this test is actually a non-parametric correlation, so it does not require the normal distribution assumption. So that's similar to Spearman correlation test. But you should use this test, the Kendall's correlation, instead of using Spearman's coefficient when you have a small data set. So when the sample size is small and you have not too many samples in your data set. To conduct the correlation test in R, so here we have the syntax. So we have this, let's say, commands or function core, and then we have different parameters or input parameters. So we have x, y, and the method. So x is a numeric variable. It could be like the sample that we have collected and contains the interval data. The same for y, and then we have the method that we should define. So we should define the correlation type. And here it can be Pearson or Spearman or a Kendall correlation. So we have to specify that in this method here. So the null hypothesis for this correlation test states that there is no relationship between the variables. So that's the null hypothesis. And once we conduct the test, then we can look at the p-value. And if the p-value is less than 0.05, then we can state that the correlation is statistically significant. Okay, so for the example of the correlation, I have a data set of people's heights, weights, and shoe size from 109 people. And of course, I've prepared the data file, which is called height.csv. So it contains the collected data. And also we have the R code, which is written in the correlation.r file. And this also reports all the performed statistical analysis to check the correlation between the different variables in our example. So let's see how we can conduct these tests using R. Okay, so now also you can pause this video and then run the video where we show the example about the correlation. After conducting the correlation test, we have to report the result of these tests. And we can do so using this following example. So we can say that there is no or weak or medium or strong. And then we say if it's a negative or positive correlation between x and y. And of course here x and y are your variables. And then we say that the correlation coefficient is, and then we put the sign if it's negative or positive, and then we report the value of the correlation coefficient. And of course, the value of this correlation coefficient will tell you if you have a no or weak or medium or strong correlation. And then we say that the p-value, we report the p-value, and we say that this is, if it's smaller than 0.05 or greater, then we have to specify that. And then based on that, we say that the relationship between the two variables is statistically significant when the p-value is smaller than 0.05, or not statistically significant if the p-value is greater than 0.05. Okay, very good. So we have arrived to the end of this lecture. And at the end, I would like to remind you that we would like to have your feedback on this module, since I've said that this module is new and your feedback is important to improve this module in the future runs. So to support us, please, you can use this QR code and answer the questionnaire. It's very short questionnaire, 3 questions. So just provide us with your feedback and we will be very grateful. Thank you. Finally, if you have any questions regarding this module, you can send me an email to this email address. And please, in the subject of the email, write that this is about the statistics model. So you can write statistics model between square brackets, and then you can add the question. Then I know that this is a question about this specific model. Very good. So thank you for your attention and good luck.